All right, today we're going to crack open a scientific cold case. It all starts with a simple question about what's at the very heart of an atom. And believe me, it leads us to the most powerful force in the entire universe. So, let's dive in.
So, let's rewind the clock to the early 20th century. There was this groundbreaking experiment that totally flipped our understanding of the atom on its head. But, as it so often happens in science, in solving one mystery, it accidentally created an even bigger one.
And this is the guy who started it all, Ernest Rutherford. Back in 1911, he did this amazing experiment where he shot these tiny particles at a super thin sheet of gold foil. Now, most of them just zipped right through. But every once in a while, one would bounce straight back. That can only mean one thing. All the atom's positive charge and pretty much all its mass were packed into an incredibly tiny dense center we now call the nucleus.
Okay, but this is where the real puzzle begins. Because as soon as Rutherford and his team started measuring these newly discovered nuclei, they realized the numbers, they just weren't making any sense.
Okay, check this out. Take carbon, for example. Physicists measured its charge, and it was positive 6. Simple enough, right? That means it has 6 positively charged protons. But when they actually measured its mass, it weighed as much as 12 protons, double what they expected. So what in the world was going on? What else was hiding in there, adding all that extra weight but no extra charge?
So you can imagine, this whole missing mass mystery kicked off a huge scientific manhunt. Physicists everywhere knew there had to be some other kind of particle in there, a secret partner to the proton, hiding inside the nucleus.
And you know, Rutherford himself actually called it. He predicted there would be a particle with about the same mass as a proton, but with zero charge, totally neutral. It took a while, but in 1934, James Chadwick finally found it. He discovered the neutron, and just like that, the mass puzzle was solved.
So there you have it. The nucleus is made of these two fundamental particles, which scientists just lump together and call nucleons. You've got the proton with its positive charge and the neutron with no charge at all. And as you can see, their masses are almost exactly the same. Now that they had all the pieces of the puzzle, physicists came up with this really elegant shorthand to describe the contents of any nucleus. X is just the symbol for the element. Z, down at the bottom, is the atomic number. That's the number of protons, which is what makes an element what it is. And A, up top, is the mass number, which is the total count of protons and neutrons together.
Let's try it out with lithium-7. That 3 on the bottom tells us right away it has 3 protons. That's its identity card. That's what makes it lithium. The 7 up top is the total number of nucleons. So you do a little quick subtraction, 7 total particles minus the 3 protons means it must have 4 neutrons. See? Simple as that. And this system is also perfect for explaining isotopes. Take hydrogen. There are actually 3 different versions of it. Now, they all have 1 proton, which is why they all behave like hydrogen chemically. But they can have 0, 1, or even 2 neutrons. That changes their mass, and this is a key point. It dramatically changes their stability.
So we figured out what's inside the nucleus. Case closed, right? Well, not so fast. Because solving the mass problem created a new, even more profound puzzle. You've got this tiny little space packed with positive protons that should be repelling each other like crazy. Why doesn't the whole thing just explode?
I mean, really think about it. It's basic physics. Like charges repel. The electrostatic force pushing those protons apart is absolutely enormous. So there has to be some other force in there, something even more powerful that's acting like the universe's strongest superglue.
And that force has a name that gets straight to the point, the strong nuclear force. It is, literally, the most powerful of the 4 fundamental forces of nature. But it plays by a very, very strange set of rules.
So here's the deal with the strong force. First, it's always attractive. It only pulls things together. And it's an equal opportunity force. It pulls on protons and neutrons alike. But here is the massive catch. It's incredibly powerful only at ridiculously short distances. We're talking distances inside a nucleus. If particles get even a little bit farther apart, its strength just plummets to almost 0.
And that weird short-range nature explains a really curious pattern you see in the periodic table. As atoms get bigger and bigger, why do they need so many more neutrons than protons just to stay stable?
It all comes down to a balancing act. That repulsive electric force is long range, so every single proton is pushing away every other proton in the nucleus. But the strong force, that nuclear glue, is short range. It only holds on to its immediate neighbors. So as the nucleus gets bigger, you have to add extra neutrons. They act like more glue, adding more of that attractive strong force, but crucially, without adding any more of the repulsive electric force. They're like the neutral peacekeepers in the nucleus.
Okay, so we've got our protons and neutrons, and they're being held together by the strong force. It seems like we've got it all figured out. But then technology improved, and scientists were able to make much more precise measurements, and they discovered one last absolutely mind-bending twist to the story.
Now this is going to sound completely wrong. Imagine you weigh a bag full of marbles. Then you dump them out, weigh each marble individually, and add up all those weights. The two numbers should be exactly the same, right? Well, with nuclei, they're not. Scientists found that the assembled nucleus was always a tiny bit lighter than the sum of its individual parts.
This was a huge problem. It became known as the mass defect, and it seemed to break one of the most sacred rules in all of physics, the conservation of mass. Mass isn't supposed to just vanish into thin air. It has to go somewhere. So where did it go?
Well, the answer came from a totally unexpected place. It wasn't a nuclear physicist who cracked this one. It was a former patent clerk, a guy who, decades earlier, had already come up with a radical new idea about what mass really is. The answer was hiding in plain sight, in probably the most famous equation in history. Einstein's brilliant insight was that mass and energy are not separate things. They are two sides of the same coin. They can be converted into one another. That missing mass wasn't lost at all. It had been converted into a truly staggering amount of energy.
And this energy has a name: binding energy. Here's one way to think about it. As you bring individual protons and neutrons together, the strong force fuses them into a nucleus. In that process, a tiny fraction of their mass is transformed and released as a huge burst of pure energy. That is the binding energy.
And the amazing thing is, it works in reverse too. If you want to break that stable nucleus apart, you have to pay back that energy. You have to pump the exact same amount of binding energy back into it. And when you do, that energy you've added transforms back into mass, and the individual pieces now weigh exactly what they're supposed to.
This incredible conversion of matter into pure energy is what powers the sun and every star in the sky. It's the fundamental secret behind nuclear power, but it also leaves us with a final, profound question. If this much energy gets locked away when we build a nucleus, what happens when we finally master the art of breaking one apart?